Okay, in the last class we discussed the two most important instruction, move instruction and then the add instruction. Along with it we looked into the different type of addressing modes that's been available in 8086 microprocessor. In today's class, let us look into what is the construct when you are trying to write a program. Following that we will just see some programs and also some directives. So, in case of assembly level programming, what you need to know is basically all the instructions, that is the mnemonics that is being used for the program along with the directives. So, as we have already seen, assembly directives are the instruction for the assembler to do certain operations, and it is not going to convert these assembler directives to any opcode, whereas all mnemonics will be converted to the machine code. So, mnemonics are instructions that are used to make the processor understand. Having just mentioned this, I think we need to really go into the details and try to understand how we go about. Assembler directives are statements that are used by the program to give direction to the assemblers about how it should translate the assembly language instruction into machine code. So, that means that there are certain points which need to be mentioned explicitly, which we have only the assembler directives can do, because the program only talks about converting it to the code to do the required operations. So, let us see what it is as we go further. So, there is a specific format which we have when you are trying to talk about programming. We have the first column, what is called as label, and here we are trying to talk about the way in which the mnemonics have to be written, and along with this we have an operand and then we have comments. Now, each one of them have certain square brackets being mentioned which says that it is optional. It means that all instructions need not have the label, and when you have a label we have label colon, and if you are trying to use the directives then we do not require these colon, we just talk about the label. When you talk about the mnemonics, some mnemonics have operands, some mnemonics does not have operands. The instructions whichever has got more than two operands, we need to have operands. The S should be there saying that there are more than one, followed by a delimiter called as comma. And then we have here the comments. So, before comment semicolon is to be given, and then we have to provide. But any program that is being written, we do not mention this particular square bracket. This square bracket is being provided only to mention that the comments can be given or need not be given. It is a good practice to give comments because it is a documentation which enables the user to understand later what you intend to do that particular instruction for. So, let us look into greater detail regarding the label. This field is optional, as I have already mentioned, trying to say that it may be there, it may not be there. All the instructions starting from this particular line need not have a label, and this field allows the programmer to refer to the line of code by name. Instead of trying to say that go to the line number 2, line number 3, etc., we have a label that enables the program directly to go, and you need not have to keep track of the line number. You need to know the label name when you are trying to write the code. And this label can be as big as 31 characters, and a label must end with a colon when it refers to the opcode generating instruction, but if it is a directive you do not have to give this particular colon. So, mnemonic is the second field what we have in when we are writing a program. All instruction must contain a mnemonic. So, that means that you cannot use some vague instruction. Say for example, when you are trying to talk about an instruction like ABD, as if you have invented a new instruction, it is not possible because there is no equivalent mnemonic for it. So, the mnemonic specifies the assembler saying that this particular mnemonic has to be converted to the required code, and they are all predefined for a particular mission. Operands may be followed by the mnemonic. Example, move AL comma BL, AL and BL are both are operands. Move is the mnemonic, and this is an instruction having two operands, and both the operands has to be mentioned. Instead of operands, there may be assembler directives also. You also tell the assembler trying to say that bring it from a particular place in a particular way. We talk about what are these directives as we go further. Today's class we talk about all the directives, that's some of the directives that are being used in 8086 assembly level programming that makes it easy for you to program. Comments, as I have already mentioned, it is optional, it is only to make the people understand, and it should start with a semicolon. Now let us look into a particular construct, how exactly we have to write a program. In this particular program, to start with, what is the format for it? The first line, I am trying to give a line number here so that if I want to refer, I will just mention line number 1 which has been set as dot model, and hence the line number is being provided, but it need not be written in all the programs. We usually say start dot model and then proceed. So the first line is to select a particular type of model when you are trying to write an assembly level program, and following this we have the next line which talks about dot data, indicates that following this particular line 2 we are going to have the data, which indicates that this has to be data segment has to be initialized, and whatever is being initialized to the data segment, this data has to, whatever is being given following it is to be loaded. Next one, we are trying to talk about dot stack. The dot stack is to initialize the stack register. If you do not give this particular statement as dot stack, say for example 64 bytes or 64 hexa dot stack 64, it directly says that the stack has not been initialized. It takes a default stack that is being provided, but it is better to give the dot stack. The following it we will have to give as dot code, indicates the start of the code segment. That means that whatever is following this particular statement, you are going to have the code of the program. So there may be a number of programs. At the end of this particular program which contains the mnemonic or the body of the program, we have the end statement. This is the end of the file. End is a statement that is being provided for the assembler to say that the assembly level program ends here. It is not, there is no opcode for end as such. Now let us go into the details of what this particular dot model means. The dot model directive selects the size of the memory model. The continuous memory available in 8086 is only 64K, so that means that you need to really look into a situation when there are more than 64K for data or more than 64K for a program, or you can accommodate both data and the program in 64K continuous memory. So that means that we are trying to mention here, giving this particular construct, saying that I am writing a program and this particular program has both data and memory in the same segment, by mentioning a very simple directive called dot model small. So short. So that means that we have a different type of constructs which we have listed in this particular table. We call this one as a tiny. It is not short, it is tiny. Dot model tiny basically says that the code and data combined together must be less than or equal to 64K. If you write as dot model small, we have a separate 64K of code and 64K of data. If you say that the size of the code can be of any size, but the data is limited to less than 64K, then we call it as dot model medium. If you say dot model compact, that means that the code is less than 64K, but data can be of any size. When you say large, that means that both data and the code both are greater than 64K, that means that it can be in more than one segment. When you say huge, it also means that in this particular case you have an array of data. This array of data may exceed 64K. When you are trying to talk about the large and huge, there is one major difference. So trying to say that the data can be available which is more than 64K, but it can be in different segments which is not continuous, whereas when you say huge, because it is an array, it is continuous and it can be greater than 64K. The next assembler directive which you are trying to give in the program is page directive. So the page directive enables you to talk about what should be the size of the page that need to be printed. That means that in a page by default the printer prints 66 lines per page with a maximum of 80 characters per line. So, in a line we have got 80. For example, I will just point out here trying to say that we have 1, 2, 3 etc. up to 88. This is line number 1. So, in a page we can have up to line number 66. 66, 1, 2, 3, 88 characters. So, that means that the user would definitely know that this is the default what is being used. But if you want to change this particular setting to something else, you can definitely do so by using the page directive. The page directive directly says that page 60, 120 directly says you can have 60 lines and in each line you can have 120 characters. So, there is a range that which you need to really explicitly know for when you are giving a page directive. The range of the line number is 10 to 255 per page, and when you say the number of columns it can be 60 to 132. You cannot have your default, the range is fixed by the assembler and you cannot exceed this. The next one is the title directive. The format is title my program. Say for example, the my program is what you want this to be as a title of this particular program which you are trying to write, and you need to give the format as title followed by my program. Note, the title pseudocode instruction is used to print on each page the title of the page, title at the top of the page. So, that means that on the top of the page you get the name of the program, and you know that so many pages you have. If 10 pages are there where your program, you have written a program in assembly level language, and each page you have my program, this enables you to understand, stating that all these programs whatever is there in these 10 pages belongs to my program. So, the title is required only if the program exceeds more than one page. If it is only one page, it is not necessary to explicitly mention that name of the program, but it is better to have the title only when it is greater than a page. The maximum size of text following the directive title is 60 ASCII characters. So, that means that you are going to have only string of 60 to give the name of that particular one. Now, we are going to the most important part of it, where we are going to define data. So, data definition directive is quite important because you need to define data and try to proceed whenever you are trying to write a program, because any operation you require, you need to really have this particular directive explicitly written. Now, to name the different data definition directives, I have just listed in this particular table and will take up one by one and proceed further. When you give the director as db, which says that define byte, it is 1 byte. That means that following db you are trying to give a number and which is of 1 bytes. Following it we can also write as dw, which means that you have 2 bytes, which is nothing but a word. dd, which is defined double word, which means that we have 4 bytes, and we have df and dp, define for pointer, which is 6 bytes. dq, define quad word, which is of 8 bytes. The last one is dt, define 10 bytes. So, we have a provision of defining 10 bytes. Invariably, we may not be using dd, dq and dt in many of our programs, because this data definition whatever we have is usually used when you are using the coprocessor. Coprocessor has a provision of trying to access this type of data. Now, let us look into the greater detail about each one of them. Now, data byte. Data byte directive is used to define a byte type of variable or a set aside one or more storage locations to type byte in memory. So, that means that whatever data you are trying to give, it is stored in the memory in the form of a byte. So, the syntax is you give a name, db, initial value, within a square bracket it is being mentioned with a comma, initial value. So, this basically means that whenever you are trying to define data byte, you can have the name which is optional, and you are trying to give the data one after the other with a comma separating one. So, you can have any number of bytes that can be mentioned. The initial value can be one or more 8-bit numerical values, a string constant, a constant expression, or a question mark. Let us see the example how we are going to represent each one of them. If the value is a signed number, it can be of the range of -128 to +127. If unsigned, the range is 0 to 255. So, the same thing is being mentioned along with the label here CHAR, char. DB, I have given character A. You can have any character you want. Whenever you are mentioning a character, it has to be mentioned in single quote, which is an ASCII character A, and that ASCII character value will be stored in the memory location. Signed 1 is again a DB. DB is the assembler directive saying that data byte, it is a smallest signed number is -128. Signed 2 DB again +127, the largest signed value. Unsigned 1, so that means that when you are trying to talk about unsigned number, obviously the sign does not come, we start from 0 to 255. So, unsigned small unsigned value is 0, unsigned the largest value is 255. So, these are the ways in which you can represent these numbers. It is possible to represent multiple values. Example list DB 10, 20, 30, 40, which we are trying to, which we have already mentioned, saying that this is an example which should be separated by a delimiter called comma. Characters and integers are one and the same from the microprocessor point of view. The same is true with respect to the assembler, and so what it does is it stores in the memory location the way you mentioned. Each constant may use a different radix. Here when I talk about the radix, it is the number system which we have. When you say decimal number system, we say radix 10. If it is binary, we say radix 2. When it is hexadecimal system, we say radix 16. So, it is possible that we can have any radix system, but we need to mention the same with in the program when you are trying to define a different radix system. The examples below give you, for example, character 1, we say A within quotes, a ASCII character. Similarly, char DB 41 hexa, 41 is an ASCII code is being taken as an hexadecimal number system and it is being stored. If you give decimal D5 without a H, it means that it takes this value as 65 decimal, convert it to hexa and store it into the memory location. Binary DB 01000001B basically says that it is a binary data. The B at the end of this particular number mentions explicitly saying that it is binary, and automatically the microprocessor will take this particular value, convert it to hexa equivalent value and store it. Obviously, we are trying to talk about all this being given to the assembler because there is no code for any one of them and it is not possible for the microprocessor to understand. So, the assembler converts it and puts it into the respective memory location. So, when you talk about octal number system, that means 0 to 7 is octal radix 8. So, DB we say 107Q, it is octal number system. It is possible to give a combination of all this different radix system, say for example 10 decimal, 20 decimal, 41 hexa, 01010110B, binary, C a character, FF hexa. So, that means that a combination of all these are possible to be mentioned when you are trying to talk about giving the data to the processor. A variable content may be left undefined by using a simple question mark. Say for example, we have a program in which you want to add two numbers and store the result in another third location. The third location value you do not know for the time being, so you want that particular space to be left aside, and under such circumstance we directly give that DB question mark. If you want more number of spaces with a comma as a delimiter separating two, we can say any number of question marks. A numerical expression can be initialized a variable with a value that is calculated at assembly time. So that means that the assembler calculates and puts the value, you do not have to calculate it. Say for example, when you want to say 10 into 10, 10 decimal into 10 decimal, 100 decimal you want, automatically it says that dB 100 is being put, 100 decimal is being put. Obviously when it stores into the microprocessor, it is converted to hexa and it is being stored. A string can also be now put into the memory location, but whenever you are trying to put the string, we are putting it in double quotes. Say for example, C string dB good afternoon with a 0 and Pascal string 14 comma within quotes good afternoon shows one string terminated by a null byte 0 containing 0 and another string with its length encoded in the first byte. 14 in the beginning says that there are 14 characters following it, which is an ASCII equivalent value, which is nothing but good afternoon. Now this particular way also we can represent and put into the memory by the assembler, and this has to be given as an assembler instruction. So assembler directives are being provided saying that it is dB. The dB directive is ideal for storing one or more lines of text. Say for example, if I want a long text to be given and at the end of the line you need to write into the second one, obviously you can do so by using dB open double quotes. This is a long string that close the quotes, that means that it considers this to be a string and converts it to an ASCII equal value for each character, puts it into a memory location. Continuation of that clearly is going to take, that clearly will be continued in the memory location if the next line continues to be a dB with a double quotes, again dB with several lines. So that means that it is possible to put all the strings which are in different lines into the memory location. At the end of it, only a 0D0A or the ASCII equivalent value which is being given for carriage return and the new line, so that it is possible for the program when you are going to execute to, after typing this particular line, goes to the new line and the beginning of the new line. The assembler can automatically calculate the length of the string, and this is done by using a dollar. The dollar character is a special character which indicates that the address of the current location. So when I am trying to talk about this, this is a very simple thing which you need to know, because when you are trying to give a set of data, you want to know what is the size of the data. The best option of trying to do this is trying to make a program calculate by itself instead of you giving the complete length. Here is a simple example with a dollar. It's being done. Example, a underscore string dB, this is a string which is given in double quotes, a length string, a length string dB dollar minus a underscore string. In this particular case, the dollar has been provided after this is a string. So the dollar means the address of the memory location after this is a string being stored is considered, minus a string is the address of the starting location, which is nothing but the a string which is mentioned here. So that means that the end of the string minus the starting location will tell you what is the length of the string. So a length of the string is initialized by 16 in this particular by the program by itself. So we have just looked into how the string integers, different radix numbers could be stored in the memory for performing the required operation. Now let us go to the next part, trying to say that how do you define double word. The values specified using DW may be 16-bit numerical numbers ranging from 0 to 65,535. So when you talk about the decimal number system, it is 65,535, but when you are trying to talk about hexa number system, it is FFFF hexa. So that means that we can mention in the program DW 1, 2, 3, these are defined as 3 words, and each one would be taken as, let me represent it on the board for your convenience to understand, that we have here NUM is a memory location which is pointing to the address whatever is going to be done is 0001, 0002, 0003 is what is going to be stored, to say that it is 16 bits. Because you have mentioned this as DW, it stores as 16 bits. So the next following it, the next location would be again 0000, and then it says 65,535. Even though it is given it in decimal, it is converted to hexa and it puts it as FFFF hexa. And this you need to understand, trying to say that whenever you are going to give it in decimal, automatically it will be converted into hexa. If you put a H along with the number, it is the same number to be stored, because it knows that it is an hexadecimal number system. Similarly, it is possible for us to store minus 32,765 when it is a signed number to plus 32,767. It is also possible to write an expression, say for example 256 into 2, and we can have a combination of all this put together 000H 4096. Whenever you are trying to talk about two characters, so A and B is put together and we have the ASCII equivalent being stored in two locations, which becomes a word. And then if you want to specifically reserve a particular word, you can put a question mark. So there are different type of combinations which you can really use when you are trying to talk about DB and DW. Now let us look into define double word, because this is hardly used until unless you are trying to talk about division of 32 bits by 16 bits. So it is possible that you can access 16 bit of data and directly store into the memory location. There are certain instructions which you will study as you go further, stating that you can move 32 bit of data from the memory location and store it into two different registers by a single instruction. Let me not discuss about the instruction set now, we will talk about the assembler directives. The double data is a 32 bits, you give the name DD followed by the initial value, comma followed by remaining value. The initial value can be a binary number up to this particular value, a segmented offset, address, a 4 byte encoded real number, or a decimal real number. So it is just only to make you understand if this has been given. Try to understand that whenever you are going to give an hexadecimal system, the assembler will not accept until and unless the first character is a numerical, because it does not differentiate between a string and the number until and unless we explicitly mention. So whenever we are trying to talk about a number being given, hexadecimal number being given, as it is given in this particular case, RAT is DD 0ABD111 hexa. 0 has been given in the beginning, even though it is not going to be stored. It knows that this is an hexadecimal number system that has to be stored. It is not a label. So it is possible to give a label in the program. This could be avoided by trying to mention a 0 in the beginning. We have defined quad word, so it is possible to really talk about the quad word, and this directive is used to tell the assembler to declare a variable 4 words in length or to reserve 4 words of storage memory. So a big number could be stored in this particular manner. Define 10 bytes, it is also possible to store 10 bytes of data, and we call this one as a packed BCD number of 10 bytes, which is being mentioned in the example here using DT as the assembler directive. Now apart from this, there is a quite important point, what is called as DUP operator. It is a directive which tells, along with DB, DW, DQ and DT, to reserve some set of memory location in the same format as DB or DW or DD or DQ or DT, enabling you not to put continuously a question mark. So DUP is nothing but duplicate. So example, NUB DB 20 DUP, and it says 0. It says that reserve 20 bytes all equal to 0, initialize these all location to be equal to 0. If you do not want this location to be made equal to 0, you want to leave it as it is, you can put a question mark saying that 20 locations, 20 bytes of locations is reserved. So this could be done as such. So, for example, you have to put characters like, say for example, ABC 4 times. So, we have here 4 3s are 12 bytes are to be used, because in this particular case A takes 1 byte, B takes 1 byte and 3 takes 1 byte, because it is going to store it as an ASCII value, and we have 3 bytes, and it says that you duplicate it 4 times. So, 4 into 3, it becomes 12 locations would be set aside, and duplication is a very convenient assembler directive to reserve bytes or to store some specific constant in the memory location. If you want to store 100 locations with 0, we can say db 100 dup 0 in square bracket, that enables you to store 100 continuous locations with 0. Similarly, when you are trying to talk about having a set of tables to be maintained, say for example, there is a nesting of this possible, trying to say db 4 dup 3 dup 0 2 dup x, the assembler assigns values in the memory as follows. So, let me explain this with on the board. What it says is, when you say 3 dup 0, it basically means that you have to assign 3 locations as equal to 0, 3 memory locations as equal to 0. Each memory location is a byte, so it is going to store 2 digits like this. Following it, it says that you have to store 2 dup, the value which is given in single quotes in memory called x. So, we have here following it as x and x. So, this will be the location to which it is going to store, but as a matter of fact, it does not go to the next line as is mentioned in the side. It continues saying that 4 times this has to be repeated. This particular operation of this has to be repeated 4 times, hence it is going to continue in the memory location as 00, 00, 00, XX and etc. So, that means that 4 times, this is first time, this is the second time, then the third time and the fourth time, and to make it look nice, I have just put it like this. If you want it in the same format, obviously you have to write 2 more, saying that carriage return and line feed should be provided in the same line, so that it performs the operation of going to the next line and display in the same format as being mentioned there. Having mentioned this, we will have to go to the next assembler directive. This assembler directive is called as PTR. PTR is being used to point, and this particular pointer is quite important, because the assembler or the assembly level program, when you are writing it, the programmer will not be able to explicitly mention to the machine whether you are pointing to an 8-bit or a 16-bit data. So, to make it very clear, you need to mention the PTR, and this PTR enables you to really understand what you are trying to talk about. For example, INC BX, it says that increment the content of the memory location whose address is given in data segment colon BX. So, the BX content is taken, added to the segment displaced, go to the memory location, and it has to increment. Now, it does not know whether it has to increment a byte, it has to increment a word, or it has to increment double word. So, you need to explicitly mention. So, to mention it explicitly, we have what is called as PTR. So, for example, increment byte PTR BX, similarly increment word PTR BX. So, this enables the user to understand, saying that it has to be either 8 bits or 16 bits. Similarly, we can also talk about byte word PTR, double word PTR, quad PTR, 10 byte PTR. So, saying that you are now considering the data as either 8 bit, 16 bit, 32 bit, 64 bit or 80 bits. There is one more important assembler directive which is very much essential in programming, which we call as ORG, originate. This is being used so that you explicitly mention to the assembler, and the assembler in turn says that the program has to be stored in a particular location in the memory location. So, when you are trying to write a program, we are not really aware of which memory location is free. We would ask the assembler to take this particular initiative and do the operation, but sometimes we know we want it in a particular location where it has to be stored. Under such circumstances, we have to give the indication saying that the program has to be stored in a particular location, and from there it has to increment. The position where the program is being stored is pointed by what is called location counter. The location counter enables the program counter to fetch the opcode and start executing the program. So, to enable this to a particular location, you use ORG, and ORG in turn will enable the location counter to be initialized to the address where it is being mentioned. Example, ORG 2000 hexa tells the assembler to set the location counter to 2000. That means that ORG is an assembler directive telling the program to start executing the program from 2000, because the program is stored in the memory location starting from 2000. A dollar is often used to symbolically represent the current value of the location counter. The dollar actually represents the next available byte location where the assembler can put the data or code bytes. The dollar is often used in ORG statement to tell the assembler to change the location counter value to its new counter value. It so happens that when you are trying to say that you want some space to be left aside and later on the data has to be stored, under such circumstances you are using this statement called ORG dollar plus 100. It means that whatever is the program where you are going to start, that is mentioned as dollar, and along from that particular point leave 100 location and later on start storing the data is going to be given by this particular statement. We have another important assembler derivative called as offset. Offset is an operator which tells the assembler to determine the offset or displacement of the named data item, that is the variable, from the start of the segment which contains it. See, this is an important set of information that enables the program to really understand how exactly you load the address of a particular variable into a particular register. Say for example, move bx comma offset prices. You would have given a label as prices, and this prices is in a particular pointing towards a particular memory location. If you want the address of that particular point where the prices is being stored to be stored into bx register, address of the location where the price is being stored into bx register, we use the instruction move bx offset prices. So, that means that there is a displacement from where this particular program counter is being set and where the price is being loaded, only the address is going to be loaded. So, having said up to this particular point all the fundamentals, let us briefly look into how the program works, how the system creates the source code and other things. So, you give any program, the program is given in an editor. So, the editor basically tries to enable you to write an ASCII code. So, the editor has to be a pure word file which does not have any special characters, it takes only ASCII code. Following this, when you are trying to have this particular program, the program name where you are going to store this has to have an extension as .asm. Once the program has been written and this program has a .asm, you give it to the assembler. The assembler assembles the program and generates what is called obj file, so it is called an object file. Along with the object file, if you want, you can also get what is called as list file. So, when it generates the list file, we get the program, whatever is the name of the program .lst. This obj file has to be linked with the library functions, if you have any library functions that you are being called, to get what is called executable file. Now, once you get the executable file. If necessary, we can put it into a debugger and start executing the program to find out any errors. If there are any error, again you go back and edit the program and the whole process continues. If there are no errors, it comes out and does that, it is fine. Now, if there is an error in your way in which you are given the mnemonic, or when your syntax error is there, the assembler itself points out and it does not produce the obj file. And once the obj file is produced, that means that your syntax are fine and your mnemonics are correct, and then it gives to the linker to generate the exe file. If your logic is wrong and if there is a problem in the process of programming, the debugger is the one which helps you to debug it and get the result, and you need to do it by using either debug or code view, whichever is the debugger is available to you, and error are to be corrected to get the right code, to get the right solution. Assemble program basically can be programmed using assembler, either using Microsoft assembler MASM or Borland program TASM. See, MASM and TASM are available in the market. So, Microsoft MASM is made quite freely available, and whoever has a Windows operating system, definitely they can use MASM and start programming. Once the program is written completely, it can be assembled to obtain the .obj file by executing the MASM or TASM, and we will look at the way in which it is being done. We have MASM followed by the file name .asm. ASM is the file which you are written using an editor, and give a enter, immediately it generates the obj file. The file name .asm file which contains the assembly line program is assembled and it is made available. The assembler generates error messages if there are syntax errors. These errors are listed along with the line number. If there are no errors, then obj file is created. To obtain the exe file, the user has to link to the obj file and get the required executable file. So, we have link file name or t-link file name has to be given. Link is used in MASM, TASM uses t-link. If the file is smaller than 64K, it can be converted to the executable file using a command that generates .com file. To create a .com file from an exe file, we need exe to bin converter. Exe to bin converter is a file which converts exe file to .com file, and exe file name and followed by another file name. This first file name is your exe file, the second file name is a file name where you want it in the form of com file. Why do you want to have a com file? What is the advantage of using a .com file? See, exe file is an unlimited size, com file is maximum of 54K bytes. That means that the size of the program is very small and you do not want to use multiple segments. Under such circumstances, it is better to have it in com file, so the space occupied by your program is less. When you are trying to talk about exe file, it takes multiple segments and the space occupied is much more. The stack segment is defined in case of exe file. In case of com file, you do not explicitly define the stack. Data segment is defined in exe file because they are separate. In this particular case, we do not even have to have a data segment defined. Code data files are at any offset address. Code and data file begins at the offset address 0100. There is a predefined position for the com file. Larger files are being obtained in case of the exe file, and small files are being taken for com file. How do you get the list file? Normally, turbo assembler produces only one file as the result of assembly, that is obj file from the .asm file. If you wish, ask turbo assembler to produce the listing file with the extension lst as well, simply by typing 2 additional commas on the command line. Example, TASM hello, we are trying to put a comma. So, in this particular case, comma will give you the list file also. This enables us to get the required exe file, obj file, as well as we get the list file. List file gives you the line number and full detail. Try it out in your lab to really get more information regarding the list file as well as obj file. See the difference, you really appreciate the advantage of using the list file. Similarly, by using the command tasm hello comma hello comma hello or tasm/i, the hello generates listing file along with the obj file by name of hello itself. So, having said this, now our next point is to develop the program, and in the next 5 minutes I will be briefly talking about it. Anyway, you need to know about the instruction set in detail, and once you know the complete instruction set, it becomes convenient for you to write a good program. And the first step to develop a program is to know what do I really want this program to do. See, whenever a program has to be written, you need to have a clarity, and only then you will have to start writing the program. You cannot directly say that I will write a program and just sit without knowing what is the end result. As you think about the program, it is good idea to write down exactly what you want and the program to do and the order in which you want the program to do it. So, it has to be logically correct. At this point, no program statement is written, but just the operation in general terms is being used. To make it much more convenient for you, it is better to use the flowchart or graphic shapes to represent different kinds of program operations. The specific operations desired is written by means of graphic symbols. So, I do not need to really explain the different graphic symbols that is being provided, especially to write flowcharts, which you have studied in the previous years, and this fundamental cannot be forgotten and you need to really follow it. Flowcharts are generally used for simple programs or program sections. Steps to convert an algorithm to assembly language is this: set up and declare the data structure for the algorithm you are working with, write down the instructions required for initializing at the start of the code section, determine the instruction required to implement the major actions taken in the algorithm and decide how the data must be positioned for these instructions, insert the instructions required to get the data in the correct position. So, having said this, I have a very simple program which makes you understand the full process. Along with it, the line number has been provided saying that 1, 2, 3, 4, 5, because that enables you to understand the process. Here the program says write an 8086, 8088 assembly level program to add two 16-bit numbers stored in CX and DX register respectively and store the result in the location addressed by DI. So, we have understood stating that there is data available and you are trying to access the data, and you can also store it in the memory location whose address is given in DI. So, let us talk about the D1 as the data 1 and D2 as data 2 and D3 as the data 3, which is of size word. So, we have declared it as, initialized it as D1 DW100, D2 DW200, D3 DW question mark, because we do not know the result yet. So, if you know the data, we would like to really understand that particular process. Try to understand here, stating that we call this one as dot model small, which is again assembler directive. Dot data is again assembler directive, stating that D1, D2, D3 are the data which is being provided. The next one is we talk about line number 6, where we have dot code. If you do not write this dot data dot code, the program will not work, because it does not know from where the program has to be converted and where the data is available. So, the next one is the move AX comma at data and move data segment comma AX. This is to initialize the data segment register with the data which we have called it as dot data here. If you are, instead of giving dot data here, if you say that here data 1, here you will have to say that move AX comma at data 1, that enables the assembler to understand that you are trying to talk about the initializing the segment register with the place where the data is being stored. So, I am initializing CX with data 1 and DX with data 2 and adding CX comma DX. After adding this, we need to store it to the memory location whose address is available in DI, but the DI is not initialized with the address. So, I am trying to initialize it using the assembler directive offset. So, move DI comma offset D3. Now, the next instruction says that move the content of CX into the memory location whose address is available in DI with data segment as the segment register. Following it, there are a couple of codes which is being given to make you understand, stating that it has to terminate the program properly. These two instructions are for DOS interrupts that enables the program to terminate normally. So, we are trying to initialize AH register with 4C hexa and we call the interrupt 21 hexa, and then at the end of the program we use end. End is a directive telling the assembler, saying that this is the end of the program, it need not assemble anything further than this. So, these are important points which has to be noted. These assembler directives are quite important for the assembler to make it conveniently execute the program without any problem. So, if there are any error in the obj file, you will have to come to that particular line and correct it accordingly and make sure that there is no error, and then proceed further and execute the program. With this, I stop here with respect to the programming. The remaining part of the instruction set and other things will follow in the coming session. Thank you.